Is it Professor Raymond Volkas?
Yep.
I wasn't sure if it was Dr. Raymond Volkas or Professor Raymond Volkas. I was thinking of that in my head this
Either
whole
is
time.
fine.
Well,
Actually,
if you weren't a doctor, yeah. Look, I've had the issue in the past with introductions, so what I'll do, I'll leave the introduction to you because I'm terrible at it. So if you could just please introduce yourself to whoever's listening and to me about your background and who you are. And I know you've got interest in piano, so if you want to add that in there too, go ahead.
Yeah, well, my name's Harrie Volkas. I'm a professor of physics at the University of Melbourne. I do research in theoretical particle physics, which I guess we'll be talking a lot about today. I also, of course, lecture. So this year I've been lecturing quantum mechanics and another subject on sort of advanced aspects of theoretical physics to third-year undergraduates. And a big part of my job is also mentoring research students, so graduate students, masters and PhD students. That's a really big and important part of my work, and a lot of the research I do is done through or with these research students. And outside of academia, yeah, I dabble on the piano. I do free improvisations, if you really want to know. Yeah, so that's sort of my main hobby, I guess.
I tried during the lockdown. I tried learning the piano, but sort of the crossing over of the fingers, I couldn't do it. I don't think I've got the motor coordination to just figure that out. I don't know why. I did try.
You know, I started as a kid, of course. My parents forced me to do it and had classical lessons for a few years, and that helps. So I don't know what it's like to start learning the piano as an adult.
Yeah, well, it's from a neuro point of view, it's very different because you got neuroplasticity in the brain as a child.
Yeah,
it's
you're
very
learning
easy
languages.
To pick things up. Yeah, it's very easy to pick things up. But as an adult, trying to force yourself to learn something, especially if you got all these ingrained habits, it's much harder. It's not impossible. Yep. It's just you got to force yourself out of some things to put yourself in another thing.
Sure.
But anyway, I digress. We'll get more on the topic of theoretical physics or theoretical particles. Sorry. What is a theoretical particle? So by theoretical, do you mean hypothetical on paper, if that makes sense?
No, so it's not theoretical particles, although it can be.
Yeah.
It's theoretical particle physics.
Yeah.
So it's about the fundamental structure of matter. What is everything made of, and how do those elementary particles, as we call them, interact with each other? So it's the study of things like electrons, which people are familiar with because that's what carries electric current. Photons, which are particles of light and electromagnetic radiation in general. Protons and neutrons, which are made of even smaller things called quarks. And most people, I think, know that an atom, which we're all atoms are, what we're all made of, and molecules. Fundamentally, an atom is a nucleus which consists of protons and neutrons surrounded by a cloud of electrons. And the study of all these elementary constituents of matter is what particle physics is. Now, there are two aspects to it, theoretical and experimental particle physics. So on the experimental side, these are people who use instruments like the Large Hadron Collider to actually get data about the way the real world
I think most
is.
people have heard of that one.
And it's not just the LHC. There are so many different kinds of experiments. Some very large, like the LHC. Others smaller, and they're aimed at different aspects of elementary particle physics. So that's a whole discussion in itself. And then on the theory side, the word theoretical is not meant to connote hypothetical necessarily. So theory is the systematization of knowledge in a precise mathematical formalism, which we call a theory. So when we say theory, it doesn't mean it's something very speculative. It just means it's a
possibility.
It just means it's a systematic mathematical formalism. So for particle physics, there's something called the Standard Model. It's it's a fairly.
Is it the 12? Is it 12, 21? It's 12 particles on the on the sample chart or something.
Yeah, you can find the usual chart easily enough through Google Images.
I have heard of it.
Yeah. So, I mean, the standard model, it's a fairly boring name, but it's a great theory. So it's a precise, mathematically precise quantum theory. Actually, it's called a quantum field theory. It incorporates relativity as well, because we have to deal with elementary particles traveling often close to the speed of light. So you need relativity, have to go beyond Newton. Anyway, it's a systematic, well-defined mathematical theory for how the elementary particles interact. And you feed in to this theory, and there are some rules that you use to construct the theory, which have been developed over a long period. So you feed the particles that experimentalists discover into the theory, and it tells you how these particles interact with all other particles that are known. So let me go through the elementary particles as we currently know them.
Please.
So first of all, there are what you might call material particles, particles that make up, that are matter particles in some sense. So I've already gone through the fact that ordinary matter is made of electrons and quarks, but actually there are 6 quarks, and protons and neutrons, which give rise to ordinary matter, are made of only 2 of those 6 quarks. We call them up and down quarks. We have funny names for these things. But as well as the up and down quarks, there are 2 partners or families or generations, as we call them. So the up and the down quark have more massive cousins, which we call the charm and the strange quark. And then there's there's another replication of this pattern, which we call the top quark and the bottom quark, which are even more massive. And in fact, the top quark is the most massive elementary particle we've ever discovered.
I'm seeing a pattern here: up, down, top, bottom.
Yeah. Well, I mean, and charm and strange. So we're a little bit playful on occasions. Now, so those quarks are distinguished by the fact that they interact strongly. So quarks are very tight bound states that form protons and neutrons and other particles like protons and neutrons that we generically call hadrons. And the force that binds quarks is very interesting. It's one of the 4 fundamental interactions that we know about at the moment. It's called the strong interaction, and it has the character that you can never knock a quark out of a proton, for example. You can try all you like, but you can't knock it out. And that's because the forces between quarks get stronger as the quarks move further away from each other, which is very unusual.
How does that work?
Well, it's like there's a string between them. Think of it as there being a string between them, and as you make the string tauter and tauter, the force, it becomes harder and harder to stretch it. And in the case of the strong interaction, that string-like force is of the nature that quarks can never be liberated. So we call this quark confinement.
Because I'm thinking of it as like an elastic band. I can imagine the elastic band, as it gets further and further, it wants to come back stronger and stronger, but eventually it will snap.
Yeah, and that is indeed what happens. Exactly. You have good insight. So yeah, these strings break, but then when they break, on the ends of these strings is a quark and an antiquark. Okay.
Like a matter and antimatter?
Yeah, matter and antimatter goes along with this. Yeah. So therefore, you still don't liberate a quark, because what'll happen instead is that one type of hadron will become, for example, 2 other hadrons or something like that. So one way or another, you can never liberate a quark. Nevertheless, we know they exist, because if you fire, for example, electrons at very high energy into a proton, you can see them bouncing off the quarks inside the proton. This is work that was done around 1970, Nobel Prize-winning work, which established experimentally the existence of quarks, which up until that point were a little controversial, because normally we expect, we can liberate elementary particles and watch them, fly through space, but it wasn't the case with quarks. So did they really exist? Were they just a mathematical fiction, or did they really exist? And it turns out they do exist, and it's just that they are stuck together in this very unusual way through this interesting strong interaction. So they're the quarks. And ultimately, the strong interaction is responsible for nuclei, So the uranium nucleus ultimately holds together, for example, because of the strong force.
Now, what were you saying about hadrons before, where if it splits, you'd have a hadron on each side? Is that what you were saying?
Yeah, well, imagine you have two quarks, and you take them further and further apart somehow. So they have this string or flux tube, as we call it, that forms between them. And yes, eventually that string will break. And on the two ends that are created, there will always be a quark and the corresponding anti-quark.
Okay.
Yeah. So the action of trying to separate two quarks is putting energy into the system, and that energy eventually goes into the creation of quark-antiquark pairs.
Okay.
All right. Now, the other material particles are electrons and its cousins. So just like the quarks have two heavier families, the electron also has two heavier cousins. We call them the muon and the tau lepton. And just like quarks come in pairs, so the up and the down quark, which form protons and neutrons,
the yin and
come
yang.
in a pair, and they're related to each other in a certain way. Charm and strange quarks are related. Top and bottom quarks are related. Similarly, electrons are related to another elementary particle, which we call an electron neutrino. And neutrinos are interesting. They have zero electric charge, so they don't radiate light or anything like that. They interact with electromagnetism very, very weakly. And they're very light. They have very little mass. So they're rather ghostly particles. But they're very important for understanding the universe. And actually, there's a lot of them about. It's just that they're going through your body every minute. Neutrinos are produced in the sun, for example. And they go through your body day and night, all the time, because neutrinos just pass through the Earth. So you get the solar neutrinos even at night passing through you.
Something you said just kind of hit a switch in my brain there, and it was so the neutrinos are obviously weakly interacting.
Yes.
Has there ever been an argument for them possibly being dark matter?
Yeah, there has been. First of all, let me just
continue what you're saying.
To say that so the muon has its own neutrino. We call it a muon neutrino, and the tau has its own. So we have this interesting structure where we have the first family, which are up and down quarks, electrons and electron neutrinos, and that pattern is replicated twice. Okay, and this three-family replication structure is still not understood. We know these particles exist, but we don't know why they exist. and you don't need those heavier cousins in order to understand ordinary matter, because that's just up quarks, down quarks, and electrons. And if you want to understand beta radioactivity, you also need neutrinos. But you don't need the other two families. So their existence remains a stubborn mystery, and it's something I've worked on and many people have worked on, and we still don't know why they're there.
So we know they're there, but we really don't know what they do or what they're supposed to be doing.
Well, so we know how they interact, because that's what the standard model is all about. But yes, if we want to, from a human point of view, assign a role to each elementary particle, so we know that electrons are there to neutralize the charge of protons, for example, and to help protons and neutrons form atoms and molecules. So we can say these things have a purpose. And electron neutrinos have a purpose because they're involved in beta decay. This is when a neutron turns into a proton, an electron, and an antineutrino. And that sort of process is very important for understanding, for example, how the sun burns. So we can assign a purpose to all those particles. With the heavier cousins, we can't. We know they exist, and we take account of them, and they affect things like early universe cosmology. All these particles, which are very rare now, and they're unstable particles, by the way. the neutrinos not so much, but the other particles, the quarks and the muon and the tau, they're unstable particles. So it's not that they're abundant. They are produced rarely, and eventually they decay. But in the early universe, they were abundant.
And by unstable, do you mean sensitive?
No, they're just unstable. So, for example, a muon will decay into an electron and a couple of different kinds of neutrinos.
Okay.
So it has a finite lifetime. It has a half-life.
All right.
It's like an unstable nucleus.
Okay.
Yeah. So you mentioned the possible connection between neutrinos and dark matter. So yeah, this was possible. It was a viable hypothesis, say 30 years ago. Okay. Because, it became clear through astronomical observations that the universe is full of an unseen material-like substance, which we call dark matter. And astronomers uncovered it because it gravitates, and it gravitates in an important way. It helps to hold spiral galaxies together, for example. It's very important for understanding the pattern of galaxies and so on that we see in the universe today. We call this large-scale structure. And without dark matter in your cosmological model, you can't understand how any of this came about, at least in the way that we have seen galaxies, sort of what pattern they form in terms of their distribution in the universe. To explain that pattern, you need dark matter. So what could the dark matter be? It's everywhere. Actually, now we know that by mass density, mass per unit volume, there's 5 times as much dark matter as there is ordinary atoms. So the stuff we understand, the stuff that the standard model of particle physics accommodates or explains, whatever word you want to use, is only about 4 or 5% of the energy budget of the universe. And there's an additional 20%, which is in the form of dark matter. And the remainder, about 75% or so, is in the form of something called dark energy, which we can touch on later if you want. But anyway, so whatever the dark matter is, it's extremely important for understanding, the nature of the universe today. And we don't know what it is. It's presumably some kind of stable or extremely long-lived elementary particle, or maybe a set of new elementary particles that are not in the standard model. They're, as we say, beyond the standard model. And it's one of the things that I work on also, and a lot of other people work on as well. It's one of the major mysteries of fundamental science, actually, the nature of dark matter. It definitely exists, by the way. We just need to identify what the hell it is. So anyway, so 30 years ago, a very economical and minimal hypothesis, and scientists like simple theories. I know science, especially theoretical physics, can seem rather complicated to lay people. It's very mathematical and so on. But it's like learning to play the piano. You have to be trained in it. And then, but we're after simplicity, believe it or not, we are after simplicity. And so we always like economical theories, So we know the universe is full of neutrinos. They were created during the Big Bang process. So the universe is full of neutrinos, just like the universe is full of photons, which we call the cosmic microwave background, which your listeners may have heard of. So now, in the standard model, when it was first written down, neutrinos were exactly zero mass particles, massless particles. So this is allowed by special relativity. Massless particles are special because they must always travel at the speed of light. You can't slow them down. You can extract energy from them, but you can't slow them down. But because these neutrinos are so abundant, if they were just given a tiny mass, a relatively tiny mass, a mass much smaller than that of the electron, which is the lightest of the other elementary particles that we know, then you could elegantly and simply and economically explain why there's this missing mass. So experiments were done at CERN. They were called the NOMAD and CHORUS experiments. My colleagues in the University of Melbourne were involved in the NOMAD experiment, and other colleagues around around Australia. At the University of Sydney, for example, were involved in NOMAD. And they searched for this very well-motivated hypothesis that neutrinos have mass in such a way that they explain the dark matter. And all their results were negative. So there's one fact. And then the cosmologists understood that actually neutrino mass would never have worked because it was not the right kind of dark matter to explain the distribution of galaxies that we see in the universe. And astronomers were starting to do galaxy surveys, and the distribution of galaxies was becoming known in precise detail for the first time. And neutrino mass dark matter just didn't work, didn't give you the right answers. And that's basically because neutrinos are very light, and so they're moving too quickly. And because they're moving quickly,
so they're hot.
They don't clump enough, and therefore it turns out when you run the mathematics, you can't explain the distribution of galaxies that we see. So now we know that dark matter has to be a completely different kind of particle. It has to be something that's not moving very quickly, so that it is able to clump under gravitational attractive force, and there is no candidate for that in the standard model of particle physics, in the elementary particles that we know about now. So this is telling us that while the standard model is a great theory, it's been tested to very high precision, many Nobel Prizes have come out of it. It's a great theory. It makes a lot of sense. It hangs together mathematically. Nevertheless, it's incomplete. It's wrong to say it's wrong, but it is correct to say it's incomplete. And it's incomplete in a number of ways, and one of them is that it has no dark matter. So we really want to know what the dark matter is. I'm often asked, if you had to name one thing you wanted to know,
what is dark matter
in your life that you don't know now, I would say, what is the dark matter, probably.
You were talking about how early particles from the Big Bang are unstable. Could it theoretically be that dark matter, because dark matter would have been present at the Big Bang, I'm guessing. Yeah. Could dark matter just be that it is also unstable and its life is just so short that by the time it's come about, if this makes sense, stop me if it doesn't, we don't have enough time to study it because it dies so quickly. If that makes sense.
It has to be very long-lived. Okay. It's either absolutely stable, like electrons are absolutely stable, or very long-lived. It's got to have a lifetime that's somewhat older than the age of the universe, which is about 13.7 billion years, because it's around today. We see it in today's universe, so it can't be an unstable particle. So what happens in the Big Bang? So the Big Bang was a very hot phase in the early evolution of the universe, and a high temperature means just a large average kinetic energy for particles. And when you have a lot of energy flying around, you can create a lot of particles. So all these heavier elementary particles I was talking about, like top quarks is the extreme example. When the temperature of the universe was high enough, if you were close enough to the Big Bang itself, there were plenty of top quarks around. And then the universe expanded and cooled, and eventually the top quarks both annihilated with antiquarks and turned into radiation, and then they also decayed away. So eventually the unstable particles disappear, and what we have left today are the stable particles like electrons, protons, neutrons, photons, neutrinos, and dark matter. Yeah, whatever it is.
I've heard of a hypothetical, you've probably heard of this, the hypothetical particle, I want to pronounce it properly, axion.
Yep.
Could you explain that to me? I've only heard of it briefly.
Yeah.
And from what I can get, it's also meant to be a hypothetical elementary particle, whatever that means.
Well, so people like me are in the business of inventing hypothetical particles.
Yeah.
So that is the sense in which theory can be speculative. Although the standard model is not speculative, and I want to emphasize that. I really kind of grates on me when I hear people say, "Oh, but it's just a theory." What they mean is, what they should say, it's just a hypothesis, and so it could be wrong. But a theory just means a systematic mathematical construct, and it may be speculative, but it doesn't have to be.
Yeah.
The Standard Model is not speculative, and general relativity is not speculative either. They're both theories. Anyway, so the axion. So actually, I'm writing a paper with colleagues and a student at the moment on axions. It's something we work on a lot. So axions are hypothetical, very light particles. They are a candidate for dark matter. So when we speculate about new particles to explain mysteries, like what is the dark matter, or how do neutrinos gain mass, or the other one, so there are 3 empirical proofs that the Standard Model of particle physics is incomplete. One is that neutrinos are now known to have a non-zero mass. We were talking about them as a dark matter candidate before, and I said they fail as that. But now we know that they have a mass they have masses that are considerably smaller than what you need for them to have constituted dark matter. So they're a very tiny, they present a very tiny contribution to the dark matter in a way that's acceptable cosmologically. But they do have mass, but it's really, really tiny. It's like probably 10 million times smaller than the mass of the electron, which, as I said before, is the lightest of the other elementary particles.
So what variable could they play in terms of dark matter?
No, they're a very small contribution to dark matter. And in fact, you can use information from the distribution of galaxies fed into a cosmological model to actually give an upper bound on the mass of neutrinos. So neutrinos cannot be more massive than what I just said, about 10 million times smaller than the mass of an electron. So they're really, really light, but they definitely have non-zero masses.
Okay.
And in the Standard Model as originally constructed, they were precisely massless. So you need to extend the Standard Model to give them mass in some way. Now, there are many, many ways of doing this. This is another major aspect of my research, is models of how neutrino mass could arise and why these neutrino masses are so much smaller than all the other ones. But it's not that we're clueless about this. It's just that we have too many ideas, and we haven't done the right experiments yet to be able to discriminate between these different theories. All right. So particle physics is an ongoing enterprise, and experiments are absolutely vital to be able to falsify theories. Now, no theorist, in a human sense, likes to have their theory falsified experimentally, because you want to be famous, right? Well, many people do. Some people don't, but most people do.
Everyone wants the Nobel Prize.
But however, it's rather an honourable thing to produce a theory that can be falsified, because you advance science that way. Your theory might have been very well motivated, very reasonable, mathematically precise, self-consistent theory, very plausible, a hypothesis worth pursuing. It was pursued, experiments were done, and it was falsified. Great. Now we know that nature can't work that way. But it's an honourable thing to falsify a theory. It's one of the ways that science progresses. So it's a good thing. We need experiments in order to drill down into what is the right direction to go in the construction of our mathematical theories. So anyway, neutrino mass is one of the 3 pillars. The existence of dark matter is another one. And that famously we know so little about dark matter. All we really know is that it gravitates, and it must be moving slowly so that it can clump under the attractive gravitational force and form structures. That's all we know. And that it doesn't interact much with photons, with electromagnetic radiation or light, and that's why we call it dark. So that's what we know. But other than that, this leaves a lot of room for what the dark matter could be. So it could be an extremely light particle like the axion, which is probably even lighter than neutrinos, although it needn't be. all the way to primordial black holes, which could have masses, something like the mass of an asteroid. That sort of a black hole is a viable candidate for dark matter. And that's such a large range of mass. And, an elementary particle with a tiny mass is a very different object from a asteroid mass black hole. They're very, very different. So, and there are lots of things between those two extremes that dark matter could be. So again, it's not that we're clueless. We have a lot of ideas, and we just need to know experimentally which, if any, of these is correct. Before I talk about the axion more, let me just briefly mention the third empirical pillar, why we know the standard model is inadequate or incomplete, and that's the matter-antimatter asymmetry of the universe. So we've touched on antimatter already. This antimatter, I think in the popular imagination seems rather weird, but we've known about it since the early 1930s. So it's a pretty commonplace sort of thing, and it just so happens that in these theories, particles like electrons have an antiparticle, which we call a positron. So a positron is like an electron, has exactly the same mass, interacts the same way, except its electric charge is the opposite.
Negative.
So electrons are negative, and positrons or anti-electrons are positive. Okay. And when an electron and a positron get together, they annihilate into usually a couple of photons. And in the early universe, you would think there should be equal amounts of matter and antimatter, because when you create a matter particle, you also inevitably create, or it seems that way, an antimatter particle, right?
Balancing wise, you would think so.
Right. However, the universe today has very little antimatter in it. We can create antimatter at great expense in accelerators like the LHC. Cosmic rays create a little bit of antimatter, but other than that, there's very little antimatter around. There's no evidence there's anything like an anti-star, an galaxy made of antimatter. There isn't gas between the galaxies even made of anti-hydrogen or anti-helium. All of that is ruled out because when matter and antimatter get together, they produce radiation, photons, and we don't see those photons. So we know there's very little antimatter in the universe today. But in the early universe, we would have expected naively equal amounts, equal concentrations of matter and antimatter. But evidently, for some reason or other, there had to be a little bit more matter than antimatter in the very early universe, shortly after the Big Bang. Only 1 part in 10 to the 10 more, very little more. But that 1 part in 10 to the 10 excess is what all the stars and galaxies and planets and you and me are made of today.
Wow.
That residual stuff. And the rest of it annihilated with antimatter and turned into radiation. And we've mentioned this already, the cosmic microwave background. Mm-hmm. That's where that came from. It came from particle-antiparticle annihilations in the early universe. These processes also produced a background of neutrinos, cosmological background of neutrinos. And that's why neutrino mass dark matter was very well motivated, because we know the universe is full of neutrinos. So anyway, a fair while ago, a very famous Soviet physicist called Andrei Sakharov, some people may have heard of him in political context. He became a well-known dissident in the Soviet Union and was even sent into internal exile for a period. Anyway, he's one of the greatest of the Russian or Soviet scientists. And in the late 1960s, he wrote an important paper where he explained the basic conditions that are needed to produce a little bit more matter than antimatter in the universe. So not a specific theory, just a framework where that could happen. So we know the general criteria that we need to adhere to explain the matter-antimatter asymmetry of the universe. But when you apply those criteria to the standard model, the standard model doesn't abide by those criteria sufficiently well to explain the matter-antimatter asymmetry. So there has to be, again, an extension of the standard model, physics beyond the standard model, to do that. So neutrino mass, dark matter, matter-antimatter asymmetry of the universe, those three things empirically, experimentally, observationally, tell us that we need a better theory. And that's what a lot of us are trying to construct. My goal in life is to hopefully play some role in the construction of this better theory. So the axion, coming back to that.
Some people have big goals, some people have small goals.
Well, some people want a theory of everything,
Yeah.
but I personally would be happy to just understand one of these three things.
That's another thing. Before we get on to axions, I'd like to ask you about the theory of everything. Stephen Hawking saying we'll have one equation that could solve it. What is that to you? I can't imagine one equation that could have an answer to everything.
Well, from the point of view of what we call the microscopic structure of matter, or microscopic physics, elementary particles and how they interact, probably there is an ultimate theory. Whether we'll ever know what it is another question, and we may not, simply because you can only do a certain range of experiments, and the ultimate theory may forever be beyond our reach. We may not have the technical wherewithal or the money to uncover this theory, because it typically involves new elementary particles and interactions and so on that occur at very short distance scales, or elementary particles that have very big masses, and these are very hard to produce in laboratories, and in fact impossible at the moment. But it's a reasonable hypothesis that there is an ultimate theory. So some physicists think it's something called superstring theory, that a lot of your listeners probably have
heard of string theory.
Have heard of. It's certainly a prime candidate. We don't know yet if superstring theory actually is the correct theory, but it's a candidate, and it's taken very seriously, and a lot of very smart people study it. There's no experimental evidence at the moment to tell us that it's true. So in one sense, there's an ultimate theory, probably. But in another sense, it won't help us with certain things. Suppose you want to understand, I don't know, the dynamics of the ecosystem of Australia.
Yeah.
Right? You're not going to turn to superstring theory.
That's what kind of ruffled me up a bit. I'm like, did you have to call it the theory of everything?
Yeah, well, of course, it's a catchy phrase.
Yeah.
So in a reductionist sense, yes, in principle, it's a theory of everything, but you wouldn't use it directly to study biology.
No.
Or even chemistry. That's crazy.
Yeah.
So all these other sciences have their own way of thinking about things.
They have their own theory of everything.
Well, they have their own. They have their own systems of thought, if you like, which require, essentially coarse graining. So if you're studying chemistry, you're not concerning yourself with what the quarks are doing inside protons and neutrons. You're not. You're mainly worried about how the electrons are rearranging themselves. So you won't be doing superstring theory if you're a chemist. Yeah. And it's just as well.
Getting back to the
axions. Yeah. So axions are a dark matter candidate. They're very light hypothetical particles. They solve a problem in the theory of strong interactions, which we opened our discussion with. I was talking about strong interactions. Now, there's one mystery about them. The strong interactions, in principle, are allowed to behave differently between quarks and antiquarks. There's a certain term in the equations that you're allowed to write down by the rules of the game. that term in the equations comes with a number that multiplies it, which is not specified by the theory. That number has been searched for experimentally through subtle kinds of experiments. If the number in front of that term in the equations was substantially non-zero, then the neutron, which is a electrically neutral bound state of quarks, would be an electric dipole. It would have a negative end and a positive end. It would be polar, if you like. So overall electrically neutral, but the negative and positive charges would be separated. So it would have what we call an electric dipole moment. That's been searched for experimentally and not found for the neutron, and also for other particles like electrons. And that puts an upper bound on the coefficient, on the constant that's multiplying this otherwise allowed term in the equations of the strong interaction. And it has to be very small, less than about 10 to the minus 10. And so the mystery is this term, which is theoretically allowed, why isn't it there? Why is it that it's nullified by being multiplied by a very small number, which could even be zero? We feel that there's something missing, that there's some other rule or some other theoretical principle that has to be brought to bear to explain the absence of this otherwise allowed term. And it's very difficult, it's very technical to explain this, and I won't even try. But the axion is a byproduct of the favored theoretical explanation for why this term is absent. This is called the strong CP problem, if anyone's interested. This proposed solution was suggested by two physicists called Roberto Peccei and Helen Quinn back in the 70s, and there's a bit of local interest. So Helen Quinn was originally a Melburnian and studied actually in my department for the first bit of her undergraduate studies, and then her family moved to the US for work reasons. So she had her career in the US. Anyway, those two people came up with an explanation for why neutrons don't have this electric dipole moment. And a byproduct of that is a very light elementary particle called an axion, which later it was found is a viable dark matter candidate. So this illustrates another thing.
So it's not hypothetical?
Oh, it's hypothetical.
Okay.
We haven't found it experimentally.
Okay.
We're looking for it. Well, not me personally, but
Yeah.
the community is looking for it. So I'll say more about that in a moment. But the point I want to make first is that this illustrates another thing that we look for in theoretical physics, which is connections between mysteries, right? So here, Peccei and Quinn were trying to solve this strong CP problem, this mystery of why neutrons don't have a electric dipole moment. And as an unexpected, surely unexpected benefit, it turns out that their theory produces a viable dark matter candidate. And at the moment, it's considered one of the major possibilities for what the dark matter could be, this axion. So we like connections between mysteries. We don't know if all these mysteries that we've talked about so far are connected or not, but some of them may be. We just have to try all sorts of different things, do a whole bunch of experiments, and then slowly uncover the truth.
All these mysteries. Should write a novel.
Yeah. Well, there's no murder though. Okay, so that's what the axion is. Let me say a few words about its status. So a lot of experiments are being done around the world to look for the axion. For a while, it was the forgotten dark matter candidate. There was another thing called a WIMP, weakly interacting massive particles. That was by far the favored candidate by many physicists. But
Would a neutron fall in that category?
No.
Neutrino, sorry.
Neutrino, no. A WIMP is a very massive particle. Anyway, so for a while the axion was the forgotten dark matter candidate, but a lot of people expected WIMPs to be discovered at the LHC, and they weren't. And also in other experiments that are looking for WIMP dark matter. And so far, apart from one experiment which has a controversial claim of detection, there's no evidence experimentally for WIMP dark matter. So therefore, your attention turns to other candidates. And a prime one is the axion. So I'm involved with something called the Australian Research Council Centre of Excellence for Dark Matter Particle Physics. This is a well-funded, 7-year initiative by the Australian Research Council, the ARC, to get all the relevant physicists in Australia who work on dark matter together to try to uncover what kind of particle it is. And within this Centre of Excellence, which involves a number of universities around the country, including mine, we're the head of it actually. There we are, not me personally, but other members of the centre are doing two kinds of experiments to try to find what the dark matter is. One kind is an experiment designed actually to test this controversial claim for a dark matter detection. And that experiment is about the search for WIMPs. But at UWA, which is one of the partner institutes, they're doing an axion search experiment. They're doing one in-house in their basement. I suppose it's in their basement. Usually these experiments are. And they're also involved with a major US experiment trying to find the axion. And there are a bunch of experiments around the world, either active or proposed. There are many proposed experiments to try to detect the axion because it has re-entered our consciousness, if you like, as a community, as a reasonable hypothesis about what the dark matter could be.
And this was a hypothesis, when did you say? Was it 30 years ago?
Yeah, it was in the 70s.
Okay, so a lot longer than 30 years ago.
Yeah.
Why was it a hypothesis then, but only being tested really now?
Well,
was it just we didn't have the equipment? Do we just not have the funding? Was that really all it was?
Actually, the story is that the original version of the theory produced an axion that interacted too much with ordinary particles, and was actually disproved experimentally almost right away.
Okay.
But then the theory was extended in a very slight way to make the axion. We call it an invisible axion. It's an axion that interacts very weakly, and that is perfectly viable. But it does interact very weakly, so you need to do very sensitive experiments. So yes, you need to develop the technology to do it. I actually don't remember when the very first axion search experiment was done, but part of the game in this area is to invent ever more sensitive ways of searching for axions.
And these are done how? With what kind of sensors are we using to try and pick up these axions?
Well, one of the main ways is that, according to the theory, an axion can interact with a magnetic field and turn into a photon, a particle of electromagnetic radiation. So that's what they're doing at UWA and in the US. They set up an instrument which has a magnetic field inside it, and they're looking for the conversion of axions to particles of light.
Right. So we know dark matter, its only interaction is with gravity.
So far.
To me, with that being said, it makes sense to find something that has a lot of gravity to test it. So, for example, I don't know, almost like is there a way we can test it interstellarly with planets that have a lot more mass than us?
Well, I mean, this is the way it was discovered, astrophysically, through its cumulative effect on the gravitational dynamics of galaxies and clusters of galaxies. I mean, the first evidence for dark matter was uncovered in, I think it was the 1930s, by a Swiss astronomer called Fritz Zwicky, who was working in the US.
Cool name. Cool name.
Anyway, he was studying clusters of galaxies. So galaxies sometimes form a gravitationally bound cluster. So you have, a bunch of galaxies all kind of gravitationally bound to each other. And what he did was measurements of the speeds of these galaxies, and he found they were moving too quickly for the cluster to stay together. The cluster should just fling apart. And so he said, well, the obvious explanation for that is that there's something inside the cluster that's providing more gravitational attraction and keeping the galaxies, which we can see through the fact that they're shining in light, together. And so he called it dark matter. Actually, he used German, and I won't try to pronounce it, but it's translated as dark matter. So that's how it started. And so he was using galaxies, which have a lot of mass, and so the fact that dark matter gravitates is how it was discovered, that it exists. But through gravitational data, like you get from astrophysics and cosmology, you will never understand what kind of elementary particle or particles it is, and then how the standard model should be extended to accommodate these new particles. We have to hope that while dark matter doesn't interact with ordinary particles very much, only gravitationally so far, that it does have some interaction with elementary particles. So let me explain a little bit how you look for a WIMP, which is the experiment there are many experiments around the world, and we're currently building one, which is going to go into a new underground physics lab, a kilometre underground in the Stawell gold mine in Western Victoria. So this new laboratory, it's the first underground physics lab in the Southern Hemisphere. Construction was completed, several months ago, and now the experiment is being assembled and eventually will be transported down in the mine. And you go underground because you need to shield the detector from cosmic rays, which are bombarding us all the time. And there's so many, the flux of cosmic rays is so great that they mask a very weak dark matter detection signal. So you go a kilometre underground so that the cosmic rays are all dissipated. Anyway, so this is a detector. The detector element in the case of our experiment, which is called SABRE, is made of sodium iodide, which is a well-known sort of detector material. And sodium iodide, like all matter, has nuclei inside it, sodium nuclei, iodine nuclei. And so what they're looking for is evidence that one of these nuclei, or maybe both, but one of them, suddenly gets a kick and recoils for no apparent reason. So, say a sodium nucleus is quietly sitting there in the detector and suddenly it shoots off. And evidently it was hit by something, but you can't see what that something was. And so you want to identify the thing that gave the nucleus a kick as a dark matter particle colliding with it. A very rare event if it happens at all, but we have to hope that it happens sometimes. You might have to watch this detector for several years to see a signal. So there's no guarantees that's the way. That first of all, that dark matter has the right nature to kick a nucleus that way. If it's an axion, that will not happen. You need to do completely different kinds of experiments, and we just talked about that. But if dark matter's a WIMP, then the sort of sodium iodide type experiment and other substances like xenon are also used. That's what you need to discover WIMP type dark matter. And of course, you have to make sure that suppose you do the experiment and you see nuclei shooting off for no apparent reason. You have to ensure that that the only reasonable hypothesis for what gave it the kick was dark matter and not something else. So you mentioned neutrons before. They are a bit WIMP-like actually, and because they're electrically neutral, and if there's a stray neutron that is produced in some way, for example, a cosmic ray liberates a neutron and the neutron zips through the detector, and it hits a nucleus, and the nucleus recoils. You have to eliminate the possibility that your nuclear recoil signal is due to what we call a background. It's a background is a phenomenon that happens that looks like the signal you're after, but isn't caused by the source that you want. So the experimentalists always have to do a lot of hard work to figure out how to eliminate all these sources of background that can mimic the signal you're looking for.
Now the ones like gravity and stuff, these are all indirect interactions, and now what you're talking about is direct interaction.
In fact, these are called direct detection experiments.
Now I heard of this maybe 2 years ago. There was an apparent direct detection, right? It was called, was it Dharma?
Dharma, yeah. So this is the controversial experiment. It's called Dharma Libera. It's done in Italy. It's been going for a long time now, a few decades. It's in a big underground lab under a mountain called Gran Sasso, east of Rome. This is one of the world's foremost underground. Well, it's underground in the sense that it's under a mountain, right? It's off a road tunnel and so on. So Dharma Libera have a very interesting claim detection of a signal, and what they used is a different phenomenon that you expect with WIMP dark matter. So WIMP dark matter should be everywhere. If it's a WIMP, and in fact if it's axions, the axions are everywhere, and these WIMPs are everywhere. They're passing through us at the moment, right? Now, over the course of a year, the Earth goes once around the Sun. But the solar system is embedded in a cloud of WIMPs, if dark matter is WIMPs. So sometimes the Earth is heading into the WIMP wind, and sometimes it's going in the same direction as the WIMP wind, because the Sun is also going around the galaxy. So when the Earth is heading into the WIMP wind, the WIMPs will produce a bigger signal. And when instead they're a sort of a tailwind.
It's kind of like riding your bike into the wind.
Yeah, right. Yeah. Exactly. And then, 6 months later, you will have a diminished signal. So you expect a direct detection signal, a WIMP nucleus collision signal, to modulate over a period of exactly 1 year and with a certain phase. By phase, I mean you get a maximum event rate at a certain time of year and a minimum 6 months later. And we know exactly when the maximum should be. And Dharma Libera have seen an annual modulation with a period of exactly a year and with a phase which is consistent with dark matter nucleus collision processes. The thing is, and it's a very, very statistically significant signal. If you ask, what are the chances that this nice sine wave, which they see, is a fluke. The answer is 1 in a gazillion. It's they've seen something, and they claim it's dark matter. However, the reason it's controversial is that a whole lot of other dark matter detection experiments have been done, which by and large should have been sensitive to exactly the same kind of WIMP.
Because they were done in a similar way.
Not necessarily, no. These other experiments that contradict Dharma don't use this annual modulation effect. They're using a different methodology. Nevertheless, they're probing the same kind of physics, the same kind of WIMP dark matter. And so there are a whole bunch of experiments that have got negative results that are in contradiction with the positive result of Dharma Libra under the usual WIMP hypothesis. There are ways you can wiggle out of this, but to most people it seems like a contradiction.
It would just be nitpicking, yeah?
Well, so the origin of the Dharma Libra signal is a genuine mystery. And one of the motivations for the experiment that our people are doing down the Stawell gold mine, and a couple of other similar experiments around the world, there's one in Spain and one in Korea, they're replicating the Dharma Libra setup and looking for an annual modulation in order to test the Dharma dark matter hypothesis using a very similar kind of experiment. So the null results from the other experiments, there's always wiggle room, because it's not exactly the same target material, for example. So you can, if you're clever enough, you can invent a way in which there would be a signal in Dharma Libra and no signal in the other experiments. It's hard to do that, but you can't absolutely discount the possibility that nature works in this unusual manner. So from a scientific point of view, from an experimental point of view, you want to test the Dharma Libra claim as precisely as possible using the same technology, because it could be that Dharma Libra made a mistake. It could be that there's a background process. I talked about backgrounds before that mimic the dark matter annual modulation signal. And while, of course, the Dharma Libra collaboration, it's a bunch of people, it's a collaboration, while they examined all the sources of backgrounds that they could think of, and other people around the world independently of them have done the same thing. And the result is they think that there's no plausible background process that can give you that same signal. Nevertheless, it could be that there's some background that nobody's ever thought of, which is very unusual. So
like a hypothetical background?
Yeah, a hypothetical background, which would be some relatively mundane, probably, process, but unusual, something no one's ever thought of. So it seems weird that would be the case.
So discovering something no one's ever thought of just by accident.
Yes. Yeah, that's possible. Or maybe they made some other mistake. I mean, we don't know. So I think from a scientific point of view, it's valid to test the Dharma Libra claim with a similar kind of experiment as possible, so that there's no wiggle room. So if our experiment gets a null result and these other two in Spain and Korea get null results, then there won't be any wiggle room. And then the mystery will remain, why is it that Dharma saw something? But we know it won't be dark matter. So let me tell you the kind of thing it could be. So it turns out that the dark matter signal phase is pretty well correlated with the summer-winter cycle. Okay? Yeah. And one thing that happens between summer and winter is that the atmosphere gets thicker and thinner. And when the atmosphere gets thicker and thinner, it affects the amount of cosmic rays that are impinging on the Earth. And therefore the cosmic ray flux also modulates annually
Mm-hmm.
with a very similar phase to the dark matter signal. So, one of the main background hypotheses is that there's something to do with the way the cosmic rays interact with the rock around the Gran Sasso lab that liberates neutrons or something that mimics a dark matter signal. And yes, it will modulate over a period of a year, and it just so happens that the phase is also the same as the dark matter signal in the northern hemisphere. And this is a good reason for why you need to do a similar experiment in the southern hemisphere, because then this seasonal effect, this winter-summer cosmic ray atmospheric thickening and thinning effect, has the opposite phase.
Mm.
So if our experiment were to see a signal, but with exactly the opposite phase from Dharma, that would indicate that it's something to do with the summer-winter changes in temperature.
Okay.
And it won't identify necessarily what that something is, but it will be very strong evidence that that's what's going on. So we need to get to the bottom of the Dharma Libra result. Is it a mistake? Is it an unaccounted for background? Or is it dark matter?
Something that's... when was this experiment done?
Oh, it was started, I think, in the 90s.
Was that when they supposedly detected the dark matter in the 90s?
That's when it first came to prominence, yes. And they've been continuing ever since.
So they actually are continuing the same experiments. Because what's kind of bothering me is when we talk about simulating an experiment but not to its exact detail. If I do, let's take an analogy. Let's say I throw a ball and the distance that I throw it just happens to break a world record, right? And then people say, oh, I don't believe you, I need to see it again. Even if I attempted it 50 times and it doesn't come back, I'll keep attempting it until I do it again. So why didn't they repeat the same experiment over and over again until they found this little blip in their radar that they found? To me, it almost doesn't make sense why they didn't try and instantly do it again.
Well, no, I mean, the Dharma collaboration did continue to take data, and they even upgraded their detector, so that's when it became Dharma Libra rather than Dharma. That's what that means.
Okay.
So they continued, but it's the same bunch of people, it's the same basic apparatus, and it's in the same location. So what we really want is independent confirmation or independent refutation, of their signal. So as I said, I mean, a bunch of other non-annual modulation experiments have seemingly contradicted their result, in terms of its dark matter interpretation. But because they're not exactly identical experiments, there's still some, in principle, wiggle room. So that's why independent physicists, our people, the people working on the Spanish experiment and the Koreans, these are all independent people. That's why it's important for those experiments to succeed and to hopefully definitively test the Dharma hypothesis. So we will see what happens.
Moving a little bit on from dark matter, we'll get a bit more onto dark energy, as we spoke about earlier on in the conversation. Can you give a small briefing to what dark energy, or theoretically, I should say, what dark energy could be?
Yeah. So first of all, as I mentioned earlier, it makes up, about 3/4 of the energy budget of today's universe.
That's why it's so interesting.
Right. So it's huge. It wasn't always the case. In the early universe, it was a negligible component of the energy budget, but now it dominates. And it's giving rise to an interesting thing. Everyone knows the universe is expanding, but rather than the expansion slowing down, as you would expect, because there's matter inside the universe and gravity is attractive, so you would think all that matter should be slowing down the expansion. But instead, the expansion is speeding up. It's accelerating. This is what was discovered by astronomers, a couple of decades ago, and in fact, the Vice Chancellor of the Australian National University, Brian Schmidt, was one of the people who got the Nobel Prize for this discovery.
I would just like to compliment you on your name recall. Throughout this whole conversation, you've just been so good at name recalls.
Yeah. Anyway, so dark energy is an unusual form of energy. It is also called vacuum energy. Now, it's not the energy in your vacuum cleaner. The vacuum in technical physics is simply the lowest energy state of a system. So here we're talking about the lowest energy state of the universe. So vacuum doesn't connote a state of nothingness. It's just the lowest energy state that the universe can be. And this state can have an energy or an energy density. And we call that vacuum energy, but it's now more poetically called dark energy. So it's about how vacuum gravitates. That's what it's all about. And this form of gravitation from Einstein's theory of general relativity, we know it has this unusual feature that it would cause an expanding universe to accelerate in its expansion. Now, what could it be? Well, there's a relatively simple thing it could be. Einstein is famous for having said that a certain thing was the biggest mistake of his life. That certain thing was
black holes.
No, something called the cosmological constant.
I think I've heard of
Yeah.
this.
So there's a certain heuristic way that you can sort of motivate the form of Einstein's field equations. These are the equations that you have to solve to understand gravity and the expansion of the universe and so on, and gravitational waves and black holes, right? Those equations, complicated equations. Now, in those equations, it's a little bit like the story of strong interactions before, where I said there was a term in the equations that was allowed, but it's multiplied, it seemingly, by a small number, which may be zero, right? And we talked about that in the context of axions. It's a bit like that with general relativity. There's a term that's allowed in the equations, which is multiplied by a number, which we usually call lambda. And Einstein called it the cosmological constant. Now, he introduced it for a reason he later regretted. The reason he introduced it is that when people solved his equations for the universe, they inevitably found that the universe was predicted to be expanding. But at the time, this was a very strange idea that the universe could be expanding. Everyone sort of thought that a static universe was a more reasonable hypothesis. The universe appears to be static if you unless you look very carefully, right? But his equations, when solved in the cosmological setting, produced expanding spacetimes. And he didn't like that. So he wanted to find a way to fiddle with his equations to stop spacetimes from expanding. And so he found the cosmological constant could do that now and produce a static universe. Now, it's not a very good static universe. It's very artificial what he did. And then Edwin Hubble, discovered that the universe was expanding. And so then Einstein said, oops, actually, I should have believed my own equations. I'm paraphrasing, but he didn't believe the consequences of his own equations. Okay. So it turned out to be a triumph. His equations say the universe is expanding, and indeed it is. Now, although he introduced it for an incorrect reason, nevertheless, that term is allowed by the mathematics. And theoretical physicists talk about this thing called the cosmological constant problem. So for a long time, what everyone thought was reasonable, both theoretically and because of the evidence, was while the cosmological constant term is allowed, the value of lambda, this number that multiplies that term, is really small and probably zero. And so the cosmological constant problem was to come up with a deep explanation for why this otherwise allowed parameter was in fact exactly zero. And it became a very famous problem because no one could think of a good reason for why it should be zero. But just intuitively, it just seemed like this was the best thing to shoot for, that it should be zero. Certainly the effects of a cosmological constant cosmologically were not leaping out at us. It wasn't obvious that this capital lambda was non-zero until Brian Schmidt and others did those measurements and proved that the expansion of the universe is in the early stages of accelerating. And even prior to that, there were some inconsistencies that had emerged in astrophysics. So, for example, some stars seem to have ages which were older than the universe itself, which is obviously impossible. But that was within a cosmology of a zero cosmological constant.
Yeah.
And if you made it non-zero, you could fix up that inconsistency. So I remember hearing talks about that even before the accelerated expansion of the universe was discovered. So the constant is there. So the most simple explanation for dark energy is that it's a cosmological constant. It's not zero, but it is extremely small. And the extremely small measurement value that's been measured for it is still a theoretical problem. It's a bit like neutrino masses, but probably more profound. Why are these things so small? At the moment, the data are completely consistent with it just being a cosmological constant. Sometimes you hear people say, in fact, you often hear it, and it sort of annoys me a little bit, that, the dark energy, it's so mysterious, we don't have the faintest idea what it is. Well, actually, we do. It's the same term that Einstein introduced, a century ago. So, it could just be that the mystery is in why it's so tiny. Okay, so that's dark energy. So it's a big topic in cosmology. It's at the interface between astrophysics, cosmology, and particle physics. And while I would argue that the cosmological constant is the simplest explanation for dark energy, it may not be the correct explanation. It might be something more complicated going on. And so one other hypothesis is that the dark energy is not actually a constant, but it's evolving. It's changing with time. That the amount of dark energy in the universe has not remained the same, but is evolving. So that the cosmological constant isn't a constant, but it's a field that is changing with time.
So it's not, as you said, it's not zero, but what it is changing, if that makes sense.
Yeah. So I'm not an expert on this, but in these kind of theories, you would try to explain through a process of dynamical evolution.
That one kind of gave me a headache.
Which?
That one, it's how it's changing like that.
Oh, yeah, well, it could be that it's a type of field. Mm-hmm. I think people are familiar with force fields like magnetic fields, electric fields, and so on. But there are all kinds of other fields around. There's a Higgs field, for example, which is permeating the whole universe. So there could be some other kind of field whose energy density is being misinterpreted as vacuum energy. Okay. And that there's something changes with time. Just like, you can have magnetic fields that change with time. You could have another kind of field that is giving rise to the dark energy, which is changing with time. It's a more complicated model for what the dark energy could be, but it at least holds the prospect of providing a kind of dynamical explanation, maybe, for why the dark energy is so small. I'm not aware that this approach has been terribly successful, but again, I'm not an expert, so I probably shouldn't say any more.
we were talking about matter, antimatter. Is dark energy just anti-gravity?
Not really. I mean, anti-gravity, as far as we know, doesn't exist. Although I understand why you ask that, because it's kind of has a repulsive character to it. So yeah, I mean, it manifests in an anti-gravity-like way, but we don't call it anti-gravity. We call it this other funny thing, vacuum energy. I mean, of course, to explain all this properly, you need to understand general relativity. So it's a bit of palaver to explain it.
So calling it anti-gravity kind of be like how do I say this? Like people might misinterpret it. As
You might misinterpret that to mean that, say, between the Earth and the Sun, there's a repulsive force, right?
Okay.
Which is not the case.
Yeah.
Right. This is dark energy.
Okay.
Is something that permeates the whole of space-time and is causing the fabric of space-time itself to expand in an accelerating manner.
Okay. Because dark matter has an interaction with gravity, with that being said, would it have some sort of interaction with dark matter? Maybe I'm only thinking that because dark matter, dark energy, but would it have some sort of interaction if it does behave like gravity in some sense?
Okay. So the gravitational effect of dark matter and of dark energy, of the gravitational effects of those two dark components of the universe are very different. Mm-hmm. Matter, for example, clumps. There's no evidence that whatever is causing dark energy that clumps. It looks completely homogeneous throughout the universe at this point, anyway. So these do look like different things. And as I say, I think the most reasonable hypothesis is dark matter is some form of unknown matter, and dark energy is vacuum energy. However, there are some physicists around the world who speculate about a deep connection between the two, an interaction between dark matter and dark energy. I know relatively little about this work, but there is some work to that effect. A mystery, if you like, today is why are we living in the epoch where dark energy is just starting to take over, dominating the energy budget of the universe and causing the expansion to accelerate. This is called used to be called the why today problem. Okay, not Y2K, but why today problem. Why are we living at this special epoch? And the energy density of dark energy versus dark matter is roughly 3 to 1, 4 to 1, something like that. So that's fairly similar, 3 to 1, 4 to 1. Maybe they interact with each other, and maybe you can therefore provide a deep explanation for why the resulting energy densities are somewhat similar. That's the kind of motivation that I think the small number of people who work on this kind of thing use.
I heard a quote once. I'd like to get your thoughts on it. It was basically how dark energy could just be, you've obviously heard the multiverse theory.
Yep.
There's a hypothetical explanation for dark energy could just be another universe's gravity interacting with ours.
Yeah. Well, no, so the multiverse...
I'm sorry to bring that up.
I have enough trouble with one universe, let alone...
Especially with dark matter.
10 to the 500 universes. So one possible explanation for the cosmological constant problem, or why the dark energy density is so small, is what we call an anthropic explanation. So here the idea is that there is no deep theoretical reason for why the dark energy should be so small, but there is a whole range of different bubbles of space-time, which we call the multiverse, each of them kind of their own universe. And in these different space-time bubbles or universes, conditions are different, and fundamental parameters like the dark energy density is different. And so these things are distributed in some way. And the dark energy in other universes has a different value, and it's much larger.
In each of these universes, the matter to antimatter could be different as well.
Yeah, it could be different. All sorts of things could be different. And then the anthropic explanation goes like this. Suppose the dark energy density in our universe was huge. If it was huge, the universe would have undergone this exponential acceleration really quickly, and there would have been no chance whatsoever for any stars or planets or humans to form. So the fact that we're around and observing and being astronomers and so on is telling us that there can't have been that much dark energy density around, because having a lot of it around is inconsistent with the existence of intelligent life, which takes time to evolve. This is called an anthropic explanation. And if you have, like in the multiverse superstring landscape vision, 10 to the 500 or thereabouts different universes that actually exist, and we live in only one of them, then, a small fraction, maybe a tiny fraction of this 10 to the 500 have very small values for the energy density. But we would only come into existence in that tiny fraction. So it's a selection effect. The fact that we have come to exist is telling us we have to be in a universe with a very small dark energy density.
It's a mathematical statistic.
Yeah, we are living in an unusual universe, because it's only unusual universes that live for long enough for intelligent life to evolve. Now, of course, this is all predicated on the existence of this 10 to the 500 or thereabouts different space-time bubbles, which are effectively different universes. This is something that seems to come out from superstring theory combined with a cosmological hypothesis called inflation. Anyway, put the two together, and it looks like this is what comes out. So, I mean, there are people that favor this kind of explanation, that there's no deep reason dark energy is small. It's effectively a selection effect. It's like, going back to the time of Johannes Kepler, right, who was one of the early physicists, in the Middle Ages, who first started constructing a systematic theory of the motion of planets in the solar system. Now, he was worried about things like, well, why is the Earth to sun distance and the Mars to sun distance certain values, right?
Oh, why is everything so perfect?
Yeah. And there were Platonic solids and so on that, he tried to use. And now we know that trying to understand why the Earth-Sun distance is a particular value is not an interesting...
It's arbitrary.
Yeah, I mean, it's an accident of complicated dynamics of a gaseous nebula that then coalesced and planets formed here and there, but there's no deep reason for any one planet to be a certain distance from its star.
It kind of just sounds like he's trying to put human meaning on it, if that makes sense. So, like,
well, yeah, I mean, at the time Kepler was working. I mean, it was a reasonable hypothesis to try that. Now we know it was a complete dead end.
What I mean by human meaning is so the Earth and the Sun are this far apart, which gives rise to perfect human creation conditions.
Right. Yeah.
So that must be like some sort of, it's just a mathematical statistic.
Yes, exactly. We have to be in this sort of habitable. Our planet Earth has to be in this habitable zone.
Yeah.
Which is why exoplanet people, are looking for smallish planets that are in the habitable zones of their stars, you know. Sure. So, yeah, I mean, the Earth-Sun distance then becomes an environmental accident. So effectively, in the anthropic explanation, the cosmological constant, or the vacuum energy or the dark energy, becomes an environmental accident. I'm not sort of super attracted to that idea, but, you know, it's one that is, you know, you can certainly construct a line of argument where that sort of explanation becomes reasonable, and it is possible. You know, I hope you know, again, it's a human reaction, but I hope it isn't correct, because I would be more satisfied with very fundamental things like the value of the vacuum energy actually having a deep reason for it, rather than it being consigned to the same you know, disinterest or lack of interest as the Earth-Sun distance.
Whereas the other equation creates more problems.
Well,
creates more work, really. I mean,
the multiverse.
Yeah.
Well, the thing is, it's kind of a logical extrapolation of superstring theory, the candidate theory of everything.
Yeah.
And cosmology, inflationary cosmology. So, you know, but it's a big extrapolation, and you know, it does assume that we've understood all of this physics precisely. And, for example, it requires the application of quantum mechanics, which is the theory, started out as the theory of the very small, you know, elementary particles and atoms and so on, to the universe as a whole. And not just to our universe, but to 10 to the 500 other ones. You know, so do we really know that quantum mechanics applies on these very large scales, or, you know, maybe it breaks down at some distant scale, you know, and we have to use something else. So, you know, I'm always wary about these huge extrapolations that are made. But if you have this hypothesis that relativity is exactly correct, quantum mechanics is exactly correct, superstrings is theory of everything, and inflationary cosmology is necessary, then put those together and you get the multiverse. I think that's probably a rigorous statement.
Well, look, Raymond, it was really good having you on the podcast. But before I wrap things up, for the listeners, if they'd like to ask you any questions, or if they would like to follow you via social media or something like that, is there anywhere that they can find you and follow your work and get in contact with you?
Well, I'm on X, the thing formerly known as Twitter.
Yeah, it's X now, isn't it? Oh man, I forgot about that. I'm not on Twitter, but I did hear that it got changed to X. But look, that's neither here nor there. I don't understand.
Yeah, that's a topic for another interview, I think. Not with me.
Yeah, definitely.
So I'm on that, and I can be found there.
Okay, on Twitter. Okay, cool.
Yeah.
X.
And it's easy enough to find my email address.
Yeah. Look, Raymond, it was so good talking to you, and thank you for this, I would say, lesson on particle physics. It was really good, and for anyone who was listening, I hope you learned something too, as well as I did. And yeah, thank you very much.
And thank you very much. I really enjoyed it.
Thank you.